Welcome to the lesson on computer systems. Upon completion of this lesson, learners will be able to describe computers and their various components and explain the central processing unit and microprocessor operation, along with their differences and similarities. Learners will also be able to describe basic microprocessor functions with the help of a simple cobot pick-and-place task example. Computers are devices capable of performing a large number of computations programmatically in a short amount of time. This means they can process large amounts of information rapidly in a predefined manner, as determined by programmers or operators. Almost all robots we work with will involve some form of computer operation, which drives data processing and decision-making for the robot. Computers work exclusively with digital signals. These signals represent discrete pieces of information, each assigned a smallest measurable unit. For instance, digital numbers can include integers or floating point numbers, which allow for decimal precision down to thousandths, millionths, or smaller increments. All computer signals are binary, operating as either on or off, high or low, or true or false. By combining these binary signals, digital information can be created, transferred, and analyzed by computers. Now, let us look at the various computer system components. The central processing unit, abbreviated as CPU, is the brain of the computer. It is a chip that reads and carries out instructions. When you click something or run a program, the CPU figures out what needs to happen and makes it happen. The control unit, or CU, is a part of the CPU, which is like a conductor in an orchestra. It sends out signals telling other parts when to work, when to stop, and what to do next, keeping everything running in the right order. The arithmetic logic unit, or ALU, is the math wizard of the computer. It handles all calculations and logical decisions, from simple addition to complex comparisons that determine if your password matches. The registers and cache memory are the computer's quick-access notepads. They hold information that the CPU needs right away, like the data you're actively working with. The main memory is the computer's temporary filing system. It holds all running programs and data while you're using them, but everything disappears when you power down. The input-output devices are the computer's connection to the outside world. They include everything from your keyboard and mouse for input to your screen and printer for output. The microprocessor, abbreviated as MPU, is the compact powerhouse of modern computing. Imagine taking all the processing parts of a CPU and shrinking them down onto a single chip. It's basically a miniature version of a CPU that packs the control unit and arithmetic logic unit together in one tiny space. While it works with memory and input-output devices just like a CPU does, these components stay separate from the MPU itself. This smart design is what makes microprocessors perfect for places where space matters, like in robot joints or small electronic devices, where they can handle specific tasks quickly and efficiently without needing all the extra components of a full CPU system. A microprocessor unit is a well-organized system where each component plays a specific role in processing data. The control unit, ALU, and registers form the main processing team, with the register unit providing quick-access storage compartments for data that the ALU needs for calculations. The memory system uses two types of storage: RAM, or random access memory, which acts like a whiteboard for temporary data that clears when powered off, and ROM, or read-only memory, which holds permanent instructions like a carved stone tablet that stays intact even without power. All these parts communicate through a system bus. Imagine a data highway where information travels back and forth, shown by the red arrows in the diagram. When the microprocessor is working, input devices send data through this bus. The control unit directs traffic, data gets stored in the RAM or in the registers, the ALU processes it, and results travel back through the bus to output devices, while the ROM continuously provides unchanging instructions. When comparing CPUs and microprocessors, there are key differences in how they're built and what they do. A CPU is a complete processing unit that comes with all the parts: control unit, ALU, and registers, plus memory and input-output devices built right into the system. It uses multiple chips and components spread across a board to handle complex operations and overall system control, like managing an entire robot's movements. On the flip side, a microprocessor takes those same CPU parts but squeezes them onto a single integrated chip. While it still works with memory and input-output devices, these stay separate from the microprocessor itself. They're not built in. This compact design makes microprocessors perfect for specific tasks, like controlling individual robot joints, handling motor control, or managing encoder feedback in real time. You can think of it like this. The CPU is the main brain handling all the complex thinking, while microprocessors are like mini brains spread throughout a system, each handling their own specific job. While CPUs and microprocessors differ in complexity, they share core functional capabilities that enable efficient computing across various systems. These include timing, fetch and execute, read memory, write memory, input-output transfer, and interrupt. Timing acts as the conductor, keeping all parts working in sync just like a heartbeat. When the system needs to do something, it uses fetch to grab instructions from memory, similar to picking up a recipe, and execute to follow those instructions, like cooking that recipe. During this process, read memory lets the system check stored information, like reading notes, while write memory saves new information, like writing notes down. All this information moves around through input-output transfer, which uses a bus network. Think of it as a highway system moving data between the processor and body parts. Finally, interrupt works like a pause button. When something urgent pops up, it can stop everything, handle the emergency, and then get back to work. Let us now look at how a microprocessor functions during a simple cobot pick-and-place task in the EV manufacturing industry, where each function plays a specific role. The timing function works like a clock, coordinating when the cobot should start and stop moving. For fetch and execute, the system first gets its instructions. Pick up battery, move to point B, place battery, and then follows these steps one by one. The read memory function helps the cobot know exactly where to pick up the battery and checks how much force it should use when gripping. Write memory keeps track of the operation by recording if tasks were completed successfully and logging any errors that occurred. For input-output transfer, the cobot receives signals from touch sensors in its gripper and sends commands to move its arm. Finally, the interrupt function acts as a safety feature. It can stop the cobot immediately if someone hits the emergency stop button or pause operations if the gripper feels too much resistance. All these functions ensure the cobot can perform its tasks safely and efficiently while maintaining the ability to respond to unexpected situations. In summary, computers process digital data using simple on-off signals to control robots and automated systems. When we look at how they're built, CPUs and microprocessors do similar jobs but are packaged differently. A CPU spreads its parts across multiple components, while a microprocessor squeezes everything onto one chip and works with separate memory and input-output devices. 5 basic functions make everything work smoothly. Timing keeps everything in sync. Fetch or execute follows instructions. Read-write memory handles data storage. Input-output transfer moves information around, and interrupt handles urgent tasks. In robots, CPUs handle complex system-wide control, while microprocessors manage specific tasks like joint control and sensor feedback. Thank you.